Hello everyone, welcome back. In this video we're going to learn about the NumpyI package, numerical Python. The NumpyI package is an extensive tool set for working with arrays in Python, and it is at the heart of efficient data science and scientific computation in Python. So as a motivation example, let's suppose we had two lists and we wanted to add them pointwise. We could go like this. List 1 equals 1, 2, 3. List 2 equals, let's say, 10, 11, let's say 10, 20, and 33. If we just type in L1 and L2, we might want this to return 11, 22, and let's put a 30 here, so that way the logical thing would be a 33. But that's not what it's going to do. If we did want it to get that, if we did want to get this, we'd have to write a function. So we could do def addition. And to be consistent with my notes, I'm just going to write addition with a lowercase a, L1 and L2. And there's a couple of different ways we can do this. Let's try to be ambitious and do it all in one line. And we could do it with a list constructor. So we could return the list containing L1 of I plus L2 of I for I in range of the length of L1. Alrighty, now let's try this one out. L3 is equal to addition L1 and L2. And okay, so now we can add our two lists pointwise with our addition function. And it's not the end of the world, but it'd be a lot easier if we didn't have to do all of that work. So the solution to this problem is NumpyI arrays. So we are going to type this line for nearly every video for the rest of the quarter. Maybe one or two we don't, but it's going to be super common. We're going to import NumpyI, which is the package we need. And NumpyI is super common, and it's almost entirely standard to refer to NumpyI by the nickname NP. So with this package, we can now say A1 is equal to np.array using the array method of the NumpyI class. Sorry, constructing a NumpyI array. So we can A1 is np.array L1, A2 is np.array L2, and let's print A1 and A2. Okay, so they look just like the lists, but they're actually NumpyI arrays. Let's take a look. Let's look at the type. Type A1. It's a NumpyI array. And what's particularly nice about this is we can just add them pointwise like this. Hooray, it works exactly the way we might want it. And we can also do scalar multiplication. So we could do 3 times A1. And this will pop out 3 times 3, 6, 9, because A was 1, 2, 3. You multiply those all by 3, you get a 3, a 6, and a 9. Now, in addition to having all of this pre-written code for us, NumpyI arrays are actually fast. So to illustrate this, let's let L1 be a list of length 1,000. One way to get this is to create a range of length 1,000. And then range type objects are not technically the same as lists, so we're going to convert it to a list using the list function. And then we're going to let A1 be np.array of L1, and A2 is equal to np.array of L2. And now we're going to use the time it. We're going to use the time it command. Percent sign time it addition L1, L2. This is going to tell us how long it takes on average to run the addition command. So on average, it took us 375 microseconds. Whereas you might recall that a microsecond is 1 millionth of a second, A nanosecond is 1/1000th of a second. So therefore, now let's try it out with Numpy arrays. We're going to do time it of just A1 plus A2. Sorry, time it, not just the time. And we saw this only took 7.32 microseconds. So we saved a factor of, okay, what's 370 divided by 7? It's like 50 times faster. And so the reason why Numpy arrays are so much faster is because the Numpy module, the underlying code is actually written in C. And C is a much lower level language, and therefore it's able to run a lot faster. So the price you pay is that you lose some of the flexibility. Python is a higher level language, so you can do all sorts of wild stuff. Like you can have a list of mixed types where we have 1, 1.0, and my cat named, I don't have a cat. Let's name my cat Mr. Bigglesworth. Okay. So this is perfectly fine, and we can check that the type of L0 is an int, the type of L1 is a float, and the type of L2 is a string. However, with Numpy arrays, everything's required to be the same type. So to illustrate this, let's let A be an NP array, and let's have it have, starting off with a list of 1, 1, 1, 1.0. All of these items are basically exactly the same, but one of them has a 1.0. So if we tried to check on the type of the first item in the list, it sure as heck looks like an int to me, but it's actually a float. Because since one item is a float, every item has to be a float. Last thing I will note for this subsection of the video is that Numpy arrays are designed to work well for numerical inputs, and you'll typically always use Numpy arrays of ints and floats. However, you technically can do this, where we could have, say, a silly Numpy array equal to np.array list, and now we should have some words. So let's say cat, zebra, giraffe, and I don't know, I like platypuses. All right, so that's allowed. And we can check that the type of our silly NP array is still an NP array. Except, what did I do wrong? I forgot the letter Y. But yeah, so our silly Numpy array is still a Numpy array. And we can even check that the type of the first entry is going to be a string. Alrighty. So now we're going to overview some more vectorized operations. So we have two Numpy arrays, np.array, and let's go with 1, 2, 3, and A2, let's have it be equal to 4, 5, 6. So as we've already seen, we can just add these pointwise. So we can do A1 plus A2, and out pops 5, 7, 9. We can even do pointwise multiplication. Something to note is that multiplication of Numpy arrays is always done pointwise. Always, always, always. And the exception and the non-exception that you need to be careful about is we're eventually going to learn about 2D Numpy arrays, which look like matrices. And so the important thing is that it's always pointwise multiplication. So just be careful that you don't, if you're trying to do matrix multiplication, you need to do something else. We're not going to get into matrix multiplication in this class, but it is something that comes up in applications. So Numpy multiplication is always pointwise multiplication. And you also have already noticed, I typed plus rather than times. But if you do type times, you do get pointwise multiplication. You can also do scalar addition. So a plus 10 is going to give us 11. A1 plus 10 is going to give us 11, 12, and 13. And A1 times 50 is going to give us 50, 100, and 150. So those are the basic vectorized operations. And there are actually tons and tons and tons of vectorized functions with the NumpyI module. So in order to use this, let's create a grid of 101 equispace points between 0 and 2 pi. In order to do this, we use np.linspace, linearly space, 0, starting at 0, going up to 2 times np.pi. That's how you get pi. And we want 101 of them. Let's take a look at x. And we can see it's a big NumpyI array of 101 equispace points. Now suppose we want to take the sign of each entry. Here, all we have to do is to type in y is equal to np.sign of x. We don't need a for loop. All we just do is we just type it in, and now let's take a look at y. So what you can see if you squint very carefully and remember all of your trigonometry is that every entry of y is going to be the sign of the corresponding entry of x. However, this is kind of hard to visualize. And actually, let's just rerun this cell so that way it looks less ugly. Let's come up with a better way of visualizing this. In order to do this, we are going to have to import some plotting tools. So we haven't really covered plotting too thoroughly yet. We're going to do this more thoroughly later. But we type in from matplotlib, import pyplot. Pyplot is our plotting package. And like NumpyI has a nickname NP, we are going to import pyplot as PLT. And then we can make a line plot by plt.plot of x and y. And we get a nice, pretty looking sine curve. As you may remember from pre-calc, this is what sine looks like. And in addition to not really requiring very much code, this is actually going to be way faster than the old-fashioned way using for loops. So if we wanted to do it the old-fashioned way, back when we learned for loops like a week ago, or maybe 2 weeks ago, we'd have to import math, then we'd write a function called listSign, and our answer would be use a list constructor. List constructors look like they're not using for loops, but they are under the hood. And so then we can make a list of range of length 100, turn A into a NumpyI array. And now let's run time it on list sign versus NumpyI array sign. All right. We had 59.2 microseconds versus 5 microseconds. And you know what? If we had done this, so it's a factor of 10. And there's what's called a cursor dimensionality, which means our time savings are going to be even bigger. Let's make this an even bigger problem. This is now 1,000. We had a factor of savings of 10. Okay, so now we have 569. But now we get down to 29. So NumpyI's arrays are faster, and when you have long arrays, the longer your array slash list, the bigger your savings are. So now we're saving by a factor of 20. Alrighty, now the big thing we do need to caution is that Numpy arrays are only faster if you use the built-in NumpyI functions. So recall we have that addition function that we defined at the beginning of the video that was not built in. Let's try this on a list versus an array. Okay, so we had 326 microseconds versus 1 millisecond. Millisecond is 1,000 microseconds. So when you don't use built-in functions, Numpy arrays are actually slower than lists because for looping over a Numpy array is very slow. Numpy arrays are fast if you use the built-in functions, but for looping over a Numpy array is very slow. So when possible, always use the built-in functions and try to avoid for looping over the entries of an array. All right, that's it for video 1 on Numpy. We will learn much more in following videos. I'll see you again next time.